All right, so today I have this cryptic title, pairwise states equal just states, and my job is that by the end of this talk, you'll actually know what this title means. Great, so the topic that we're actually going to talk about is magnetic monopoles. And for me, although magnetic monopoles could have some non-abelian or string theory structure at their core, for me, they're just point magnetic charges. And what I want to do, the thing I care about, is how do you quantize QED plus monopoles? How do you write an action for that? How do you quantize this action? And how do you compute scattering amplitudes of monopoles and charges? It turns out that a monopole, or any particle which is magnetically charged in the presence of other particles which are electrically charged, modifies the Hilbert or space of quantum multi-particle states of the theory. So it's not just like a new particle. There's asymptotic interactions between magnetic charges and electric charges that completely changes the definition of the S matrix, leads to new selection rules on monopole amplitudes that were never seen before, and actually leads to new quantum numbers or helicities in the scattering of charges and monopoles, which are contrary to anything that we know in physics, are quantum numbers associated with pairs of particles, charges and monopoles, rather than with single particles. So that is kind of a completely different ballgame from what we usually know about the structure of the S matrix. And in this short talk, I would like to invite you into this world and see its peculiarities, and specifically all kinds of features that arise, like topology, group theory, and how they're intertwined with one another. Good. So for me, even though there's a non-abelian core, the monopoles are just point-like magnetic charges. And of course, because QED, or even just electromagnetism, forbids the existence of magnetic monopoles, when Dirac first wrote these about these objects, he imagined that there's this string of flux that's very, very thin and should be unobservable in any experiment. So this is kind of a mathematical device, a gauge-dependent feature, which shouldn't be detected in any experiment. And of course, we could take a wave packet or a particle and take it in a full circle and look at the phase, okay, the interference between what we started with and what we get after a full circle, and that will compute the flux, the magnetic flux carried by the Dirac string. And that should be unobservable. But that exactly leads to this quantization condition, which means that Eg, the electric charge of the particle that we took around the circle, times G, the magnetic charge of the monopole, over 4 pi should be quantized in half-integer units. So that's the conventional argument for Dirac quantization that we know and love from undergrad quantum mechanics. Another feature of a system where there's a charge in the monopole can be seen completely classically, and this is something we usually don't learn about in undergrad, even though J.J. Thomson already computed it in 1904. So this is not a mistake. It's something very cool that I wasn't aware of until a few years ago. So if I just take a classical magnetic charge and a classical electric charge, and now I compute the Poynting vector in all of space, and I do r, the radius, cross the Poynting vector, that computes the angular momentum that's inside the electromagnetic field. And notice that I'm talking about angular momentum, but the monopole is static and the charge is static. And yet, when you compute it, you see that there's extra angular momentum in the system equals to minus Eg times r hat. That's the direction between the monopole and the charge. So this is distance independent. I now throw the monopole to another galaxy. There's still some angular momentum linked to the pairing of the charge and the monopole. And of course, this extra angular momentum is going to modify classical scattering, just going to change the angular momentum of the system. And it's also going to lead to modified selection rules on quantum scattering amplitudes. So let me kind of share with you some of the overarching themes of the past few papers that we wrote, and also this dates way back into some papers by Defects. So one question is, what is the action for electrodynamics plus monopoles? We said that Maxwell's equations sort of forbid the existence of monopoles. So how do you properly write a quantum theory which is identical with QED when it talks only about charges, but is able to also host monopoles in it in a quantum way? And also, how do we quantize it? So there were several attempts, and in '71, Zwanziger wrote a beautiful model which has charges and monopoles. It's just like monopole QED. And the idea is that the coupling of the monopoles to the photon is not a coupling to A, the photon, it's a coupling to A tilde, the dual of the photon. Now, these are not two different particles. This is just rehashing of the degrees of freedom of the photon into a dual vector potential. So there's always just one photon, but it has two descriptions that fit together to write an action for the coupling of monopoles, charges, and photons. The other questions that we ask are, what is the space of quantum multiparticle states with contain charges and monopoles, given that extra angular momentum that we don't really know how to place it in the context of the quantum S matrix? This leads to this question: what about the angular momentum? And also, what is the role of Dirac quantization in the quantum field theory? And what is the role of the Dirac string? So we've had quite a few papers about it, and some of our intuition comes from pioneering work by Zwanziger in the '70s. Good. So this is what we'll talk about today. The first thing to note is that because of this extra angular momentum, by definition, the quantum state of a charge and a monopole is not equal to just the direct product of the charge and the monopole, because an angular momentum operator would just pick up the sum of the angular momentum individually of the charge and the monopole. But where's the extra piece that's linked to the pairing of them under the electromagnetic field? So already we know that this is weird. It's not a Fock space. So what is it? How do we define charge-monopole multiparticle states? And somehow we should reflect the extra angular momentum. So in the series of papers that we wrote, based on pioneering work by Zwanziger, we realized that the multiparticle states of charges and monopoles actually have extra pairwise velocities. These are exactly the quantities that are quantized by Dirac quantization. And there's one for each pair of charge and monopole, or two diodes in the multiparticle state. And these quantum pairwise velocities, they reflect exactly the addition of the angular momentum to the multiparticle state. And in our papers, we define them formally. So the way these things transform under a Lorentz transformation, this is the unitary representation of the Poincare group on the multiparticle state, or the Lorentz group. It has the usual factors that are associated with each particle individually. SU2 little group for a massive particle, U1 little group for a massless particle. But it has these extra things that link everything in a pairwise way. And there's a phase here, which is called the little group phase. And these are pairwise velocities. This is what is Dirac quantized. Of course, this modified transformation rule, when I construct the S matrix by contracting together an in state and an out state of this variety, will lead to modified selection rules, which we took advantage of in our follow-up work. But before sharing the results, let me kind of drill down a little bit more about what this pairwise little group is, because we'll need it later for a more quantitative analysis. Okay, so consider a charge monopole state. And I'm taking them to be scalars. So there is no spin quantum number. The only characteristics of the quantum state is the momentum of the charge, P1, the momentum of the monopole, P2, and this associated Q12, which is just E times G over 2 pi. How do I define the transformation rule of these quantum states under a Lorentz transformation? The first thing that I do is I go to the center of mass frame aligned with the z-axis of the two particles. And now I ask myself, what is the subgroup of Lorentz transformations that fixes both these vectors at the same time? It doesn't change any of them. Well, of course, these are just rotations around the z-axis. They're common axis. This is what I call the pairwise little group. It's just a U1 of rotations around the common axis of the two momenta in their center of mass frame. Now, as soon as I have a U1, I can label representations of this U1 with helicities, Qij, exactly what the Dirac one is. So if I want to represent a unitary rotation around the z-axis on these reference states, this is represented by just e to the I, the label of the representation, the helicity, times the phase that I rotated. So this is the definition of the relevant representation. And now I can ask, well, I want the quantum state of any momenta, not just these K1 and K2. How does this state transform? Well, the answer to that is that we need to somehow boost from this center of mass frame to the finite momentum frame. And we define a canonical Lorentz transformation that takes the reference momenta to the finite momentum. And then it's very simple to show that under any Lorentz transformation lambda, the unitary representation of lambda acting on the quantum state would just be lambda acting on the momentum, but an extra factor here, which is equal to acting with the canonical Lorentz transformation, so reference momenta to finite momenta, then acting with any lambda that I want to represent, and then going back. So when I do this, what I'm tracing in orientation space is kind of my orientation goes full circle. And there's actually a geometric phase. I'm subtending a portion of the sphere in orientation space. And the solid angle in orientation space is exactly this. This is like a geometric phase. So anytime I have a little group, I'm basically picking up the geometric phase, so the Lorentz transformation of the states. And now more quantitatively, because we'll need it later, this Lorentz transformation that takes K1 and 2 to P1, 2 is not uniquely defined. It has some freedom. And I can choose to fix this freedom by choosing a random direction, n, which later we'll see plays exactly the role of the Dirac string, and demanding that this entry in the canonical Lorentz transformation is basically the epsilon contraction of P1, P2, and this random direction n. So this line of the canonical Lorentz transformation is orthogonal to n as a 4 vector. Then I can kind of crunch the numbers, it's just a computation, and I can get an exact expression for what this phase is. This is, to remind you, is the phase that the quantum state of a charge in the monopole accumulates when I do the Lorentz transformation. So the cosine of this phase is like the dot product of these two vectors, which are the epsilon contractions of P1, P2, and the Lorentz transformed direction, or now I'll call it Dirac string, with the untransformed Dirac string. So I know this was a little quick, but we'll soon see that the important thing to know here is that this definition was pure group theory or representation theory. There was no QFT in it. And then for the rest of the talk, I'll just do QFT with charges and monopoles. I will actually calculate the loop amplitude. And what I find is exactly this. Okay? So the group theory and the QFT somehow marry and unite in the middle. But first, a little bit of what we did with it. I told you that using these quantum states, we can, they're modified angular momentum selection rules. And we utilize these selection rules to derive all 3-point amplitudes of monopoles, reproduce very counterintuitive effect like the forced chirality flip. If a right-handed fermion falls into a monopole, it has to come out as a left-handed fermion in the S wave, which is very counterintuitive. This is a selection rule that happens 100% of the time. We reconstructed monopole spherical harmonics by dotting together new spinors that transform under the pairwise little group. In other words, we derived geodesics and Taubner, which is kind of like the gravitational analog of a monopole, as the classical limit of our pairwise amplitudes. Recently, we've been working on defining pairwise states, not just for charges and monopoles, but also for extended objects, somehow to construct their S matrix and realize that there's Dirac quantization and an extra angular momentum also for branes, which are mutually non-local. And finally, we proposed an on-shell derivation for monopole catalysis. That's what's called the Kalin-Rubikov effect, which once we establish the formalism is just a one-liner. It's just saying the only amplitude that preserves angular momentum selection rules And standard model quantum numbers is calendrical. It's monopole catalysis. Good. So let me get to the main point of the talk. We posted this, the pairwise states. We derived many interesting results, but there was still a lingering question. What are these mysterious states? Am I really, do I really need to do this kind of confusing pairwise group theory to define the Hilbert space of the theory, and then somehow I get all my results by magic? So we've been thinking about it quite a lot, and we've been hoping for a simple answer. And we actually got it. So the simple answer is that pairwise states are just the IR dressed charge monopole states. So we know that to solve the QED IR problem and to get a well-defined S matrix, we have to dress our asymptotic states with soft photons, with basically a photon cloud. And what we discovered is that when you do this dressing, just for not just QED, but QED with monopoles, you get quantum states that exactly have this pairwise feature. So this mysterious pairwise link between charges and monopoles, which was defined abstractly in terms of group theory, is simply the fact that they talk to each other with soft photons. And even asymptotically, they have kind of like the electromagnetic analog of a Coulomb potential between them. So just flashing the math very quickly, dress states are simply Baire states when acted on with a dressing operator. This is a time-ordered integral of the coupling of the electric current to the photon. And from now on, I just need to crank the numbers. So this generates a retarded and advanced electromagnetic field, if you know from undergrad, the Leonard-Vikert potential associated with charges here. This is QD. And when you unravel the time-ordered product, you see that there are actually two operators here. There's an operator which dresses the asymptotic states with real photons. And there's a phase which is linked to an exchange of virtual photons between the two charges. The charge monopole version of this is exactly what is going to give me the pairwise helicity, the extra phase. All I want to do is do it with monopoles. So now instead of just J and A, I have J dual and A dual. And when I plug in the mode expansions for the photon and for the dual photon, like I said, there's one photon with two descriptions. So these are the same creation and annihilation operators with different polarization vectors. Now, all that's giving me is the sum over all ladder diagrams that exchange the pink photons between the charge and the monopole. And what I want to show is that exchange shifts under a Lorentz transformation exactly by the pairwise phase that we got from group theory. And that's indeed what we showed. So just glossing over the details, we substitute the mode expansions and we calculate commutators. And we find that indeed this extra phase is something like the integral over the ladder exchange of soft photons between the charge and the monopole, which is equal to this really nice integral. All that remains is to calculate this Feynman integral, and then we got stuck. Okay, so this integral, just by Lorentz invariance, is supposed to be, this k here will be substituted by either P1, P2, or n, but there's an epsilon contraction. So this seems like 0, but it's actually 0 over 0 and needs to be regulated. And we were on this, we regulated this, we worked on this for a while, and then my collaborator, Ziyu Dong, who's very good, he's a student at the Beijing Center for Theoretical Physics, who's spending the year at Cornell. He had simply a brilliant idea, not a long time ago. And the idea was, even though this integral is 0 to 0 and needs regularization, what we're interested in is actually not this phase, but it's the delta of this phase when we do a Lorentz transformation, which rotates the momentum. And paradoxically, though the integral needs regularization, the difference, the delta, actually does not. It's completely finite, as he demonstrated elegantly. He just put it on Dropbox. It doesn't matter what I said. I read it and I was like, okay, I was an idiot. You are right. This integral doesn't need to be regulated. And he showed it to me in position space by Stokes' theorem. And then after we realized that, we did it in momentum space, and we found that this integral evaluates very elegantly just the four-dimensional solid angle subtended by the directions of the momenta, the Dirac string, and the Lorentz transform Dirac string. And once we symmetrized, we found that it's exactly equal to this expression you saw before. So the Q of T and the group theory marry together and give the same results. And that as a proof, we also have a proof by other means. That the address states of quantum electromagnetic dynamics are equal to the pairwise multiparticle states. As a bonus, you could ask, okay, this weird soft photon phase looks Dirac string dependent, but of course we said the Dirac string is unphysical, so somehow we shouldn't be able to measure it in an interference experiment. So what if I tried to force it? What if instead of just scattering, I created a charge and an anti-charge, and they kind of went in full circle and met here. And I calculated the soft photon exchange with this entire closed path. It turns out that in this case, as Turning and Verhaeren, my collaborator, Christopher Verhaeren, showed in 18, topology comes to the rescue. And the result actually becomes 2 pi q times an integer. Q is Dirac quantized. The integer is the topological linking number linking the charge world line in this world sheet of the Dirac string in 4D. So this is exactly the Q of T generalization of the original Dirac quantization argument. And that's my conclusion.
Questions for Ofri?
Right. So thanks for the beautiful talk. So you basically demonstrate that once you resum properly the soft photon between charge and monopole, there's all of a sudden extra angular momentum introduced. Do you have a quick argument to why if we do the same thing with the electron-electron or monopole, there won't be extra angular momentum?
I think there will be. It's just perturbative. So you can take, I mean, the E squared contribution you can just take as an extra. For example, there are loop level corrections to the soft photon theorem in QD that go like E squared, and they enter exactly where the angular momentum operator would be. So that makes me think that there is actually a correction. But just for QD, you don't care about it. And here, because E times G is Dirac quantized, it completely changes the structure of the.
Okay. Does that, on the other hand, consistent with the quantization of this angular momentum? Because it doesn't look like you can change smoothly, but rather you just either turn on or never turn on. Right? It's quantized.
Yeah. So I'm a little hesitant to answer that. It might be that the angular momentum is actually not modified in the QD case, but when you do the soft photon theorem, the E squared contribution enters where a angular momentum would come in. Okay. But let's talk about this point. By the way, Segwu is my collaborator on the 2 first papers. Yes.
Yeah, my question is related, I guess. You interrupted something that looked like it matches the group theory, and the group theory statement so how should be exact. It's like it just be some set of ladder diagrams. Because it's not perturbative, it's not good. How do you know that there aren't clear diagrams? So is there some kind of monumentalization theorem or
it's a dressing factor, so it's all the numbers.
Could you repeat the question, please?
Oh, yeah, it was just Matt. Can you repeat that?
Yeah, I'm saying that the group theory statement is an exact statement about the angle. But this calculation didn't look obviously exact. So I'm wondering if there's some non-normalization theorem or some argument that sort of gives you.
So the answer to that, it is exact. It's not perturbative. I'm not resumming diagrams. It's like an iconal calculation. So
right, but that's still iconal calculations are usually some approximation.
Not if it's a dressing factor, because in the dressing factor, what you're doing, you're peeling off the soft photon contribution when energy of photon really goes to 0, not just like expanded around 0. So you're really taking the T goes to infinity, energy of photon goes to 0 contribution. And that is all orders and is exact.
I have another question, which is, have you tried to do any of this with runs or with data transfer?
No, very interesting.
Because in particular, John had previously made a direct claim about
I'll be happy to talk about it. Yeah, no, we have not addressed data terms.
Yeah, so normally, I mean, when, we do reservation theory, we always say that, it's not possible to have a weakly coupled theory that includes both charges and monopoles, just because, the magnetic charge is the inverse of the electric charge. So one thing is weakly coupled, the other one is strongly coupled. So we typically resort to, we think of the monopoles as some kind of extended soliton. So, if I were to think of this, your monopoles are sort of like, as you say, like from the distance, everything just looks like point-like. But, if I insisted in realizing the monopoles as, some simple version of like the topological monopole, something like that. Does all of these come out somehow out of the, non-abelian structure of SU2, or like what do you learn from?
I think it does, because this is just the asymptotic structure, right? So and
I guess do you learn anything new from taking like another step and actually?
Well, let me put it this way. We have modified angular momentum selection rules that in some cases are very stringent, like they tell us that there's a helicity flip, or that there's monopole catalysis. So that's a really strong claim. And now, to be really, really sure, we can just open the box and do the field theory. And if the world makes sense, the field theory will choose to populate the one outstate that survives the angular momentum selection that we pose. So it's like an interplay of the microphysics and the macrophysics.
So we have a question on Zoom as well from Oliver. Oliver, please go ahead, unmute yourself.
Hi, yeah, thanks for the nice talk. I wanted to ask about crossing symmetry. So if we imagine an electron-positron pair annihilating, and then there's some intermediate state, and then at the end we have a monopole-anti-monopole pair, the in state or the beginning state and the final state don't have these selection rules. Their QIJs are all 0, but the crossing symmetric version of that has an electron and a monopole, or a positron and an anti-monopole. And yeah, so how will crossing symmetry work in this setup?
Great question. So that's actually funny, because when we didn't think about it as electromagnetic dressing yet, that was like a big riddle. Like, we defined these multi-particle states, and when we combine them to create an S matrix, it seemed like it was not crossing symmetric. So that was a big mystery. But actually, once we are saying, due to the conclusions of this talk, that pairwise states are equal to dress states, we know that dress states are actually not crossing symmetric, or at least not trivially crossing symmetric in this theory. So that kind of uncovers why, like, we indeed don't have crossing symmetry, because we have this angular momentum associated with a Charge-Monopole pair, but if we flip the leg, we just don't have that angular momentum. So you're right, this is another peculiarity of the system.
Thanks a lot.
I have a question. Go for it.
So, so two things. One is a simple clarification. When you talk about the pairs and having like a phase between them, is the pair enough, or do you need to have also triplets and quadruplets, because they're also interacting with each other, right? So somehow the pair enough to.
Yeah, so it's always pairs. From the group theory perspective, it's clear, because if you're trying to find the subgroup of Lorentz transformations that fixes 3 momenta at the same time, it's nothing. So there's no triplet and further little group in 4D. From the QFT perspective, yeah, direct quantization comes in pairs. And also the dressing factor. So okay, so the dressing factor has density operators that pick up the momenta of 2 particles at a time. So that's another explanation why it's only pairs.
And the second comment I have is that this way of thinking about it as a dressing and therefore connecting it to making QED IR finite and connecting it to software. There's a whole industry of asymptotic symmetries that people have thought about, which is about U1, but it's also about non-abelian theories and about gravity. And so if there is a way to understand this effect that you guys are finding out in terms of dressing, it might just connect to the whole other line of work. But then you can generalize this to maybe, much more than just U1. So I don't know if you thought about it.
Yes, this is how we got there. So we started by writing the asymptotic symmetry paper. Then we said, oh, it's referencing some unknown paper that we're going to write. So we first wrote this, and now we'll have them both.
I see.
All right, let's thank Ofri again.